So I'm going to talk about G1 garbage collector, which was introduced in Java some years ago as a replacement for concurrent merge sweeps, so CMS collector. And it is designed for bigger heaps, big heaps like 8, 12, 16, 40 gigabytes. And like CMS, G1 attempts to address the old generation pauses. So it's nothing about young generation. We don't care about young generation pauses. We try to optimize the old gen. So at the beginning, let's get to know each other. My name is Jakub Kubrynski. I'm working as a professional software development. As a professional, so I'm talking about the time when they started paying me for my job for over 11 years. Now I'm a co-founder of DevSkiller and CodeArtist startups. At DevSkiller, we have created a platform which allows you to test candidates' coding skills before inviting them for a job interview. And this evaluation is done in the target environment, consists of libraries, frameworks, and technologies used in your organization on a daily basis. So if you use Gradle, MongoDB, and Postgres and Java, we can test candidate across all these skills. Also, I'm a JVM passionate, and I conduct trainings in performance tuning and Spring at Bottega Company. And now I would like to know a little about you. How many of you are Java developers? Okay, how many of you are analyzing the garbage collection logs or something like that? Okay, about half. And how many of you does some JVM tuning on a daily basis? Okay, like 10%. So why should you even think about sitting the next 40 minutes in this room? So why do we need all this stuff? Mostly because our applications needs memory, and memory is limited. We are not allowed to allocate. We have to clean up this memory on some time. And as a developers, we are usually too lazy to manage this memory manually. So we need someone or something to do it for us. And there's a job for garbage collector, but garbage collector has a limited performance, and usually it needs to stop the word to do its job. And sometimes this stop the word pauses, something we call the GC pauses, is no problem for us, but for bigger heaps, it can take seconds, dozens of seconds, something like that, which even for a classic web application is something that's unacceptable. Yeah, we don't want our users to wait 30 seconds after clicking something on a web page just to let our application do a garbage collection, okay? So generally speaking, garbage collection is something that is very easy. We have garbage collectors in PHP and C++, in Python, etc. And it's classic scalar algorithms. By scalar algorithms, I'm talking about the reference counting. Yeah? So I'm creating a new object, assigning this object to a variable, then assigning to other variable, etc., etc. And I'm counting how many different variables or different objects are pointing to mine. Okay? When this reference count is equal to 0, it means that my object is unreachable, so I can close it, okay, and destroy it, forget about it. So, do you know what are the drawbacks of the scalar algorithms that don't allow us to use scalar algorithms in Java? I have a DevSkiller cool T-shirt for someone that knows. Okay, continue. Isolation, exactly. You want a T-shirt. Okay, so the answer is islands of isolation. So when we are tracking the references, we can have a situation where we have object A pointing to object B pointing to object C, and object C pointing to object A. okay? And no other objects are pointing to this island of isolation, but it cannot be cleaned. So in Java, when this island of isolation could be half of our database loaded by Hibernate, and it's, let's say, 2 gigabytes of heap, it's unacceptable to let it down. In C++, it just happens. Okay, so we are not allowed to use scalar algorithms, so we need to move to vector algorithms. And the vector algorithms are also really simple. Yeah? We start by marking all GC roots. What are GC roots? These are objects that are live by a definition. So live threads, used monitors, system classes, class loaders, etc. So if we know that this thread is live, it's doing some job, we know that it can be treated as a garbage collector root. Okay, after marking all GC roots, we are starting from each root found in a previous step, and we are marking all objects that are referenced directly or indirectly from this root. Okay, so we are moving through all objects that are visible from this particular root, and then for each object in memory, we are checking if this object is marked as reachable, and then we are unmarking it to prepare for the next cycle, or else, if it's not marked as reachable, we are removing object and reclaiming the memory. Okay, and that's all. It's really simple, as you see. We will be probably we probably could implement that in a few hours. Okay, so what's the problem? Why guys in Java are doing it for many years? So the problem is that this algorithm is, of course, very simple, but it's suboptimal for bigger heaps. Probably such simple algorithm won't work even for 500 megabytes heap. But for 4 gigabyte heaps, so these are heap sizes for which the J1GC is designed, it won't work at all. So we need to do some tricks to speed up this algorithm. And there are a few different tricks or approaches that we can use in Java, and we are using it in Java to speed up this stuff. First thing is something called the generational hypothesis. It's based on something called the infant mortality, which tells us that if you refresh your memory and bring back childhood memories, you will probably agree that we are all here due to unbelievable fortune. Yeah. So if you look at this girl putting scissors into electricity, it could make some problems. So in Java, we assume that young objects are very likely to die really soon. Okay. And so if we are allocating objects, this object will probably die in the next 2 or 3 garbage collection cycles. Okay, so we count the age in Java objects in garbage collection cycles. And after certain thresholds, note that this threshold is configured as a tenuring threshold flag. These objects that pass this particular threshold are said to be long-living object. So if object has survived 7, 6, 12 garbage collection cycles, it's treated in a different way compared to this newly created objects. Okay, so that's the first idea. Those objects are behaving differently, so we can process both generations separately. The next thing is something that is called card table. Okay, we are going to process both generations in separate, okay, but the problem is that it's not common situation, but it happens that parent points to the child, okay? So we have an object in old generation which points to an object in the young generation. So to see or to check if the object in the young generation is still reachable, we would have to check all this old generation if there is anything that points to young generation, okay? And that's something that's unacceptable for us. So the guys from GC team has introduced something that is called the card table. Card table is just a set of cards, and each card is tracking the 512 bytes of the memory in old generation, and it checks if this slice of memory is pointing, has any pointer to the young generation, okay? So then we are using something called the write barrier, and if this card is dirty, then we know that during the young generation collection, we need to check these 500 kilobytes of memory to check if there are no pointers to young generation. So we are checking not the whole old generation, but only this generation we've marked with cards marked as a dirty. Okay, but it's still not enough. There is still a lot of work that GC has to do. Okay, there's no option that we will resign from some work. So the idea is to process all this work, or almost all this work, in parallel or concurrently with our application. So we don't want to stop application, do all the GC job, and then renew the application threads. We just want to make our application work concurrently with garbage collector, okay? And this is the first trick, third assumption that we want to use here. Okay, so now I'm going to talk about ways of freeing memory in the heap. So we have a situation before collection. These dark places are dead objects, and lighter blue are live objects, okay? So now we want to clear the memory, and we have two ways to do that. First is something that the algorithm called mark sweep. So we are just sweeping these objects from the memory, and we are keeping something called a free list. It's a list of free spaces in memory that we can use to allocate new objects, okay? So that's the first algorithm. Second is a mark compact, okay? We are not only freeing the memory, but we are also compacting the heap. And both of these has pros and cons, okay? So here, freeing the memory is really fast, but allocating new objects is not so fast, because at the first we have to find a new place where we can put our object, okay? And of course, if there is big amount of memory, we don't want to put small object here, because in this situation we can have a option when there is, for example, 100 megabytes free memory, and we are not even able to allocate 1 megabyte object because this memory is splitted. And here, allocating objects is really fast, because we are just bumping the pointer to the beginning of the free space. But compacting the heap is something that is really costly. So there is something called a copying algorithm, which is used, as you probably know, in the young generation for the garbage collection for a long time. And we have an hidden here and two survivor spaces, okay? So I'm doing one thing. I'm marking the objects that are live, and I'm copying those objects to a first survivor space, okay? Then I'm filling hidden one more time marking the objects, but instead of sweeping these objects, or instead of compacting them, I'm copying those objects to a new survivor space, okay? So, brilliant. There is no compaction, okay, but there is the heap is compacted, okay? So great algorithm. Any drawbacks? Do you see any drawbacks of this algorithm?
You got still S1 or S0 is always empty, so you will take more memory that you really need, and there's also problem of overflowing when there are cases where these objects do not fit in one of the survivors.
Exactly. So the base problem is that we need twice as much memory as we would need to without the copying. Okay, so we need to have some place that we can copy our objects. So for survivor spaces that can be, I don't know, 16 megabytes, 400 megabytes is not a problem, but for whole heap, when this heap is around 60 gigabytes, it's not so easy to get, oh, I need just another 60 to use a copy algorithm, okay? So with G1GC, they've decided to split the heap into many small heaps, let's say, okay? What does it mean, many? It depends. For up to 4 gigabytes of memory, we have a fixed size of each heap region, which is 1 megabyte. So for 1 gigabyte, there will be 1,000 regions in the heap. For 4 gigabytes, there will be 4,000, etc. Usually, it's around 2,000 up to 4,000 regions. So as you see, it's a lot, and the regions are still similar to those that we are familiar from the classical algorithms. So we have hidden, old generation, survivor, but there is also something called humongous. Okay, if I split all this heap, and then it means that if each of these regions is 1 megabyte, I'm not allowed to allocate, for example, array which is 10 megabytes, okay? So to do that, I have to join 10 regions to create something, a space called the humongous space. It's space for these big objects. Okay, and so let's see the garbage collection in action. After all hidden regions are filled up, we are starting the young generation collection. So we are processing all young generation regions, like hidden and survivor spaces, and we are copying those objects to another 3 regions. So here we have created old generation, here survivor space, here another survivor space, and after that we are freeing all these regions because all left objects were moved to new regions, so this slice of memory can be freed up. So we've freed, and now we are starting with allocating new hidden regions. Okay, so it's similar to normal situation, but we are working on a separate regions. Okay, so what's now different with the previous situation? In a classical garbage collector algorithm, we are tracking the card table. Okay, so we are marking dirty cards for each region pointing to the young generation. But here we have thousands of heaps, okay? So it's not so easy to track all this stuff. So they've changed the way of, they've implemented that stuff, and we have something that is called the remembered set. Remembered set is in fact like a card table for each region, okay? So it records references from other regions to objects in that particular region. So there is nothing about the old and the young generation. We're just tracking the references between different regions, okay? So in fact, the regions remembered set consists of card of addresses to different regions, okay? And this card contains location of reference that points into that region. And what we now have to do is to concurrently actualize all these remembered sets, so R sets. And in garbage collector, in G1 garbage collector, this is done concurrently by something called the refinement threads, okay? If you will start working with G1GC, you will work directly with something called the refinement threads, so something that is actualizing all this stuff here. Okay. Another important terms in GC is collection set. Collection set is a set of regions that are going to be collected during a GC pause. Okay. So this is the number of young generation survivor spaces, old generation that are put into this C set. Okay, so we are not clearing all the memory during a GC pause that we used to do previously, but we are clearing just some part of the memory. Okay, and it's calculated by some heuristic we can track it, we can control it, etc. I will talk about it later. There is also something called root regions, and these are regions with survivor objects pointing to old generation. Okay, so we are talking a lot of different phases in G1. Okay, so now we are marking something, we are copying, we are doing some refinement of this remembered set, etc. So what are the real collections in G1GC? Okay, there is of course something called Young collection. That is obvious, it's in every generational algorithm. But there is also something called background concurrent cycle, mixed collection, and full GC. Now I'm going to talk in details about each of these different types of collections. So starting from the Young GC, it's of course triggered after filling all hidden regions. So we are allocating new objects. When all hidden regions are filled, we are starting the Young collection, which is parallel and stop the word. As you can see, there is nothing about the concurrent collection of Young generation. In fact, there is no concurrent Young generation collector in a hotspot. Okay, so all algorithms are stop the word in Young generation, which sometimes makes a problem, sometimes no, because Young collection is usually small, so it won't be a problem. Okay. And so there is nothing new in Young generation, but there is something called a concurrent cycle. And concurrent cycle means that it's piggybacked on Young GC. So it's done during a Young GC pause. Okay, so the Young GC stop the word. So when it stops all the application threads, the concurrent cycle is doing the initial mark. If you are familiar with the concurrent mark sweep algorithm, those phases are some kind similar. So we still have something called initial mark. So we are marking, finding all GC roots, etc., etc. Then we are finishing the Young GC. So we are releasing all the application threads to start working with our application logic. But the concurrent cycle continues working. Okay, it's tracking all the references, checking if these objects are live, etc., etc. And this is a concurrent root region scan and a concurrent mark. Concurrent mark, the same as in a CMS. And this is also can do something called concurrent cleanup. So it can concurrently clean some regions, but these are really rare situations. So let's say that it's cleaning really small amount of memory. But why do we need all this concurrent cycle? In fact, there is no such thing like old generation collection in G1GC. Okay, in CMS we have young generation and old generation, and in G1GC we have young generation and mixed generation collection. What is a mixed generation? So mixed GC is cleaning young generation and some part of old generation. What does it mean that some part? Okay, we've done this all concurrent marking phase, and now we are going to clean some old regions during the young generation phase. Okay, so we are not collecting all this giant old application heap. We are just getting some part of it, and this part is usually calculated that in minimum it's number of regions marked in the previous step divided by the G1 mixed GC count target flag value. Okay, and in maximum it's 10% of all regions. By default, G1GC assumes that it will execute 8 mixed collections in a row. Okay, so we are doing called the young generation collection. Now we see that our old generations start to fill up. Okay, so we are starting the concurrent marking cycle, this background cycle, which has found let's say 40 or 50% of all generation regions that can be cleaned, okay? So now we are starting this mixed generation that is cleaning all young generation plus some part of old generation, okay? After a few seconds, we are starting another young generation, and we are cleaning different part of the old generation, etc., 8 times in a row, which allows us to clear all this old generation during the young GC phases, okay? So there is this really small amount of time needed to clean up just few regions, okay? But there are some situations that the garbage collectors cannot process whole heap using this mixed GC, and then it triggers something called full garbage collector, full GC, okay? Full GC is really huge problem in G1 because it is really slow serial collector, okay? It's not even parallel. So for bigger heaps, if you will see full GC, it can take minutes, okay? It's really big problem. If you have a web application and garbage collector takes 4 or 5 or 12 minutes to finish, okay? So it's, and of course it cleans everything. It cleans meta space, code cache, etc., okay? So, is there anything we can do to tune up the garbage collection JDD2015? Of course. And it is designed to be really easy, okay? They are saying that everything you have to do is to set the max GC pulse millis, and GC will try to do everything and to do its best to fit this time goal, okay? So here you said that each pulse cannot take more than 250 milliseconds. Great, yeah? Yeah, but the dark side is that it won't work in many cases, okay? And if you see that it doesn't work, you have to use some part of those flags to tune up the GC. And as you can see now, it's not so easy, okay? You have to really deeply have really deep understanding of the G1 to be allowed to tune something and to gain something with this tuning, because it's easy to add some flags and see that garbage collector is working slower than before, okay? So then tuning is really fast. Just remove all the flags you have added and it's faster, okay? But are there any good practices or quick wins that we can use? Of course. So at the beginning, there is flag called initiating heap occupancy %, okay? Which means that if we see that the concurrent mark cycle is starting too late, okay, it's not able to scan all heap before memory fills up, okay? Because what happens when we are concurrently marking all this heap, the application is still working, so it's still creating new objects, okay? So we are trying to find all these objects that are live, but application is creating the new one. So then when the add-on is full and we have no free memory, then it's something called concurrent mode failure, and we are starting this full GC, okay? So stop the word, serial collector, 12 minutes later, we are get back to work, okay? So if you see that the concurrent mark cycle is not able to process all this stuff, just change the initial heap occupancy % to let this concurrent mark cycle starts earlier, okay? So that's first thing that you can do. Second thing is that if you see that this concurrent marking cycle is starting in the right moment, but it's working too slowly, okay? It takes too long. Then you can change the concurrent GC threads to make GC able to use more threads, okay? So then it can split the word not for 3 or 5 threads, but for example, use 10 threads if we have a huge CPU in our case, which allows it to finish the work faster. Okay. Next thing is you will see something called two-space exhaust, which means that GC needs more memory. Okay, it needs more free memory to work effectively. So there is something called G1 reserve % that we can change. Okay, and we are saying, okay, we need 10% of free memory just for GC, that it will be able to copy objects into new spaces because we have free regions here. Okay, and the last thing is there is a phase called the reference processing. And this reference processing is usually taking too long. And no one knows why. There is flag called parallel ref proc enabled, and it's turned off by default. Okay? So the first thing you can do always is just enable this flag, and it will speed up your garbage collection in G1. Okay? I hope it will be default, but we will see. Next, I've told you about the humongous object. So what's the problem? If the object is bigger than half of the G1 region size, it will be treated as a humongous object. And the problem is that humongous allocation can cause full GC, okay? Which is a problem for us. If you're allocating a lot of big arrays, big strings, etc., you will have all the time full GCs, which, as you remember, can take minutes, okay? So how we can fight with humongous, because we know the humongous is evil, yeah? We want to eliminate them. And how can we eliminate humongous objects? If we have a lot of arrays for 4 or 5 megabytes, what we can do is to change the region size to 10 megabytes. Then those objects will fit into normal region. We don't need still humongous regions to keep these objects. Okay, so this is first trick, and it can speed up your GC throughput for, I don't know, 30%. So it's worth to know about it. What else should you look for? There are 3 problems. First, the concurrent mode failure. I was talking about this earlier. Second is a promotion failure. It happens when GC has no more old generation regions that it can put all these objects here, okay? So we are doing the young generation. I want to promote my objects because they've reached certain tenoring threshold, but there is no old generation space. So I have to clean up the old generation to be able to clean it. And there is also something called evacuation phase, and it also can reason in full GC because we are not able to, there is no space for survivor spaces, okay? So I want to evacuate my objects from Eden to survivor spaces, but there is no space for survivors, so I need to execute the full GC or retenure the regions from the survivor to old, okay? And now I'm talking that you should look for promotion failure, you should look for evacuation failure, you should check if this concurrent mode, concurrent cycle was started in the right moment, etc. But how, okay? There are really verbose logging in G1. As you can see, this is the medium level of logging. You can configure it to be finest, so to contain more information. And as you can see, we have a lot of information. We see that this is GC pause, and it was caused by the evacuation. It's taking some time. There is parallel time with 8 workers, etc. So all phases and all information is can be found here. Okay. Also, because as you can see, these logs are really verbose, so it's hard to find something meaningful here. So you can use tools, such tools like GC Viewer, JVisual VM, or Mission Control. All of these tools are working properly with G1. So you can get the G1 logs, put it into GC Viewer, and you will get the throughput, the pauses, all the statistic information about the heap right in the table in GC Viewer, okay? Is there anything else that you can use, okay? So still, throughput or parallel GC, it's still the best GC if you don't care about the pause time, okay? If you are going to process some background work and you have, I don't know, a lot of stuff to be processed in Hadoop or something like that, or to put something into Cassandra, and you just want it to finish as soon as possible, then you always use the parallel GC. It's always the highest throughput, okay? But still, it can cause the one pause only, but this pause can take a few hours, okay? But still, for the whole work, it will be the fastest. We have the concurrent merge sweeps or the CMS, but it's there is nothing new coming into this GC. All efforts are in G1, and CMS is just a legacy collector. And there is something called the Shenandoah. It's the garbage collector, the Red Hat garbage collector, and they are working on something it's called the pauseless GC. The pauseless GC means that they are trying to have a 10 millisecond pause for each 100 gigabytes of heap, okay? So it means almost pauseless, but the problem is it doesn't work for now, okay? So we have to wait some more time for that to finish. And you probably heard that G1 is going to be a default garbage collector in Java 9, okay? So the discussions in the GC mailing group, here you can see the abstract, okay? Using GC is known to corrupt Lucene indexes. Does the term known imply past tense? Okay, so do it seriously. And then Stefan Johnson said that, okay, the change to make G1 the default garbage collector has now made its way to Java Dev and soon be a part of early access build. So, okay, we know that there are some problems, but we don't care about it, it's default, okay? So still, as you remember, I said at the beginning that G1 is designed for bigger heaps, like 4 gigabytes, something like that. It's not said that it will be better than, for example, parallel GC for your IDE or for small applications. But in Java 9, it will be the default, so just remember about that. Okay, that's all. If you have any questions, I think we have a few more minutes, so we can try.
Hello, have you used yourself or seen someone using G1 in production?
Okay, so the question is if I use G1 in production. Yes, we use G1 in production for more than 1 year, and it's working really stable. And even for applications with 8 or 12 gigabytes of heap, it's working faster than CMS, and it's still easier to tune G1 than CMS. So CMS is not so easy to tune, and you have to have a really deep knowledge, okay? In G1, it's common then it's faster than CMS without any tuning, and if you want to tune it, you can do, let's say, 60% of the tuning using those flags I showed, not on this one screen, but this particular few flags. And if it's still not enough, then it's hard to tune it more. But still, it's the easiest to tune G1 because sometimes it's this pause goal is enough to work for you.
Is it a web application that you're?
Yes and no. So this is web application, but also some application doing the backend processing of events. Any other questions? No? Okay. So thank you very much, and see you on the after party.
Thank you very much for the lecture.